All right. So what do we do if we want to build a grammar simulating the moves of a non-deterministic pushdown automata? How do we actually do that? Literally the shortest thing ever. All right. With the last few minutes of class, now that we've teleported ahead a few minutes for those watching back to the lecture video, we've gone over an exam, and now we're going to continue talking about the conversion between NPDAs and CFGs. But then what after that be accepted? So what we're trying to generate now is, given a state machine, how can we parse the state machine to be able to produce the grammar? So it's a very similar train of thought here. So the stack is going to contain the non-terminals of the grammar, again, just as they did the other way around, except now what goes on the stack is going to be whatever the NPDA sense the stack symbol is. Whenever we have that same stack symbol, we want to represent that same non-terminal. So we'll make a couple of assumptions. There is a single final state in the NPDA that can only be entered if the stack is empty. We can show that any NPDA that we could construct could be constructed as such. The other is that every single move must either increase or decrease the stack count by 1. So we cannot have a pop a character push that exact same character, a stack no-op. We either must be pushing or popping to the stack. We can also show that we can reconstruct any NPDA where we do those things with an equivalent NPDA where we do not. If you're curious about that exact process, the textbook goes over it, but it's kind of the mirror of what we already went over. I feel like if you intuitively understand one, you'll probably understand the other, and it's not too bad. What I do want to cover and talk about is a deterministic pushdown automata. It's not as straightforward to convert an NPDA into a DPDA as you might think, for the reason of there are 2 variables. In a regular language, in an NFA and a DFA, there was really only one variable, the character that you were reading in the input string. But now we also have the stack operations that we are doing. So we get a tuple on a change of the input character that is read, which could be empty, and the stack change that we are doing, which could also be a no-op. But for determinism, we actually have to allow for what's going to look like non-determinism at first, but is not actually non-determinism. Which means that if we have that tuple of an input symbol and a character that is on top of the stack, there must be a predefined move for that tuple. But that does not mean that there only needs to be one path out of a state if on a particular input symbol. So let's say we're reading an A. We can have 2 transitions out of a state on an A as long as they're looking for a different top of stack character. Which means that we can use lambda transitions. If we don't consume an input character, but make a change to the stack, that is legal. If we make a change on an input character, but don't modify the stack, that is also okay. We just can't do both. So why do we still allow lambda transitions? And that's because the state is defined as that tuple. You are modifying the state if you're changing either the character you're looking at in the input string or what is on top of the stack. So the only real non-determinism comes from if you're going to do neither of those. Or if from a given state, you're able to get to 2 possible states from that same tuple. That's what's going to define non-determinism from this perspective. Do you have any questions or thoughts on that? Yeah.
So you're going to have edges equal to the cross product of your alphabet and your stack alphabet.
Yeah, it can get large. It can get kind of gross. So we know that the definition of determinism is basically at most 1 possible moves exist at 1 point in time. Given that you are looking at a character, have a particular symbol on top of the stack, you can only make 1 move. When we were talking about DFAs and NFAs, we found that they were perfectly equivalent to each other. However, there is no such conversion. We cannot convert an NPDA into an equivalent DPDA because they actually represent different classes of languages. Some NPDAs will have an equivalent DPDA, but there's no easy way to know that off the top of your head. So I think we have time for a quick example. Here are a couple of languages. First language, A to the N, B to the N. Second language, A to the N, B to the 2N. Think about, why is the first language context-free? We actually showed that it was context-free, but why was that? Think about, how do you solve that problem with a stack? Push something for all the A's, pop those for all the B's. Done. How about the second language? When we see an A, push 2 of those things. When we see a B, pop 1 of those things. And then if we reach an empty stack, there were twice as many B's as there were A's. So now let's define a new language, the union of those 2 languages. Is the union context-free? How did we determine that we could use a union and figure out whether that was context-free? If we look at the left-hand side and figure that that's context-free, you can assume that there is a context-free grammar that represents it. If the right-hand side is context-free, there will be a grammar that represents it. All we have to do is introduce one new rule now that says the new starting state for the grammar is the starting state for the left-hand side or the starting state for the right-hand side. Done. You have defined a grammar that represents the union of those 2 languages. That makes sense? How are we doing with that? Yeah.
By definition, they're disjoint. Is there any language that will satisfy both? Exactly.
Yeah, so I guess when n equals 0, so they both accept the empty string. So you can imagine now that there are 2 different grammars. We had the concept of S1, arrow, etc. Doesn't matter what else, but this accepts L1. And L2's grammar is S2, arrow, something, and the rest of it doesn't matter. All we have to do to get the union is we say introduce a new rule that is S arrow S1 or S2. And you put that in and combine all of these in a single grammar. And now we have a way of saying we can get to the first half, we can get to the second half. Great. But what tells us which one of these to pick? Because we need deterministically, when we see the first character, in order for this to be deterministic, we need to know, are we in the left-hand side or the right-hand side? What's the first character, unless this is the empty string, what's the first character we're going to see regardless of where we are? An A. Given that we see the first A, are we in L1 or L2? No clue. We can't make that distinction on this character. So even though this is a context-free language, we can't deterministically tell where to go when we see that first A. So this is an intuition and an example for why NPDAs map to context-free languages as we've described them, but DPDAs are a subset of that language. There are some context-free languages that don't have a deterministic pushdown automata for them because we can't tell from the first character or the first sequence of characters which of a union we are in. And some languages will be able to be broken down into an equivalent union. So even if it's not described as a union, you can convert it into a problem that is a union. I'm over time by a couple minutes, I apologize. So we'll come back to this next week and finish off this before we dive into the context-free pumping lemma, which I'm sure we're all really thrilled about at this point. So I will handle any and all exam questions right now.